Hi everyone, and welcome to our first lesson video in our new unit, Unit 3. The title of Unit 3 is Applications of Derivatives. So we're finally going to explore where you can use derivatives in the real world. So our first lesson, which we will actually be on for a few days, is our related rates introduction. So I thought it would be good to start with what the heck a related rate is. So the title of this is related rates, and if you think about the word related rates, rates which are related to one another. So here's the definition off the internet. It says, in differential calculus, which is what you're studying, related rates problems involve finding a rate at which a quantity changes by relating that quantity to other quantities whose rates of change are known. The rate of change is usually with respect to time. And there's all sorts of problems that we're going to explore in this lesson that's going to last several days. But today, we're actually going to do the classic falling ladder problem. You will find the falling ladder problem in every calculus book I've ever seen. So that's where we like to start. Everything you do today will have to do with this type of a problem. This is how I'm going to teach it. And then your assignment will also be all about falling ladders. So let's go ahead and read it first. I'll read it out loud as you read it with me. It says an 8-foot ladder is leaning against a vertical wall. If a person pulls the base of the ladder away from the wall at the rate of 0.5 feet per second, so there's a rate, then how fast is the top of the ladder moving down the wall when the base of the ladder is, and then we've got different options here. We're going to do it when the base of the ladder is 3 feet from the wall, 4 feet from the wall, 6 feet from the wall. Okay, so the reason, again, this falls under related rates is we're looking for a rate. How fast is the top of the ladder moving down the wall based on the fact that we know that the ladder is being pulled away from the wall at a known rate. So we're going to be able to use this known rate to find the rates that we seek. Okay, so I've brought a template here, and I highly suggest you setting up the same categories here for related rates problems. Now, the reason I'm doing it on scrap paper is because I didn't think I would have enough room here. So I'll just transfer some of this work over here once I have it sketched out. Kind of like drafting final copy. Okay, so the first thing I always do, my first heading is a diagram. So I want to do the best I can at drawing a picture of the situation I just read. So I am going to draw an 8-foot ladder leaning against a vertical wall. So I'll make my vertical wall right here. That's my wall. It's vertical. And then I'm going to draw a ladder leaning up against that wall. So this will be my ladder right here. Can even make it really look like a ladder. I'm no artist, but feel free to make your drawings as fun as you like. Here's my ladder leaning against the vertical wall. And of course, the wall and the ladder are both going to have to meet the ground or the pavement or whatever, the floor. So I'll draw that as well. And this is creating a right triangle where the vertical wall meets the floor. So that seems like a good diagram. Now, given that diagram, I like to kind of couple my diagram with this heading, what I'm given. So let's go back into the reading here. The first thing I'm given is that the ladder itself is 8 feet long. So that's definitely something I can put onto my drawing. So I've got this 8-foot ladder. So I'm going to go ahead and make that 8 feet. And the cool thing about related rates is that when you have values that are unchanging, you may place them right on your drawing. So the length of this ladder is not going to change. No matter how much I pull this way or it falls down the wall, that is unchanging. So I'm going to go ahead and assign that its numerical value. Okay. Now, The next sentence says, if a person pulls the base of the ladder away from the wall at a rate...
Interruption. 10th graders,
Hold on.
A through L. If you purchase a photo package on picture day, August 30th, and are unhappy with your picture, please bring your package with you and report to the auditorium. If you are a new student or a student that didn't have your photo taken or didn't purchase a package in August and would like to do so now, please bring your order form and payment envelope with you to the auditorium. Again, students, 10th grade, last names A through L. Thank you.
Okay, sorry about that. It's picture retake day here at Conestoga Valley, so we might be interrupted several times with those announcements. Okay, so basically, we have a rate here. So we know that the rate at which this distance right here is changing, this distance is growing 0.5 feet each second. So here's this person down here pulling the ladder away from the wall, and this distance is increasing 0.5 feet each second. So what I like to do, because this is a changing value, like this distance, wherever it starts here, it's going to grow. So I can't really assign a numerical value here, so I'm just going to go ahead and call this x. And then what's cool about that is I know that the change in x, which I like to call dx, with respect to time. Now check that out. We're used to doing dy dx from the last chapter, the derivative of y with respect to x, the change in y with respect to x. This is how quickly x is changing, the change in x, as time goes by dt. And that is given as 0.5 feet each second. The x, this guy right here, is measured in feet and time in seconds. So I'm given that. Okay, let's read on. How fast is the top of the ladder moving down the wall? I'm going to highlight that. How fast is the top of the ladder moving down the wall? So I'm looking for how quickly this distance is changing per second. So because again, this is a changing value as the ladder slides down, this distance right here shrinks. So I'm going to go ahead and call that y. And so what I need to figure out is how quickly y is changing with respect to time. That's what I don't know. What is the change in the distance y over time? Let's question mark that. My units will be feet per second because y is measured in feet and time in seconds. And the other thing I'm given is this last part. How fast? Okay, when the base of the ladder is. And then we have these three values. So I'm also given that in part A, my x value is 3 feet from the wall. In part B, my ladder is 4 feet from the wall. And in part C, my ladder is 6 feet from the wall. Okay, so that kind of captures the reading of the problem. Got my setup. I know x is growing. I know y is shrinking. I know x is growing at this rate. I want to figure out how y is shrinking at these different values. So exactly when this distance is 3 feet, exactly when this distance is 4 feet, and exactly when this distance is 6 feet, how fast is the top of the ladder coming down the wall? Okay, the next part of this related rate is the equation. So we've got to get something rolling here where we relate the variables with what I'm given and what I need. So I see a whole lot of x and y's here. a whole lot of x and y's, and the equation that I know that's going to relate the x and the y is simply the Pythagorean theorem. So I'm going to go ahead and relate x and y through this diagram with this equation. X squared plus y squared equals 8 squared, which is 64. Well, that's all fine and dandy. But as you can see, this equation has absolutely nothing to do with time. So we are now going to force, see my hands there? Force time into our problem. And there's a really easy way to force time into the problem. What you do is you implicitly differentiate your equation with respect to time. So what I want you to do is bring your equation over here under the title of differentiation. And I want you to just go with me here for a second. Remember when we first learned to implicitly differentiate, when we found dy dx, we did it with respect to x. Well, now we're going to implicitly differentiate with respect to time. So it's going to look like this, term by term. We're going to differentiate with respect to t. So we're going to find d dt of x squared plus d dt of y squared is equal to d dt, of 64. Okay. Now, one of these I can do right now. I can do the 64. You can differentiate a constant with respect to whatever variable you like, since there's no variable with a constant, and so that's simply 0. These two are going to prove more difficult. How will I differentiate x squared with respect to t? Like, I can't do that. The variables don't match. So I'm going to use a technique that I used in the last unit when we first learned implicit differentiation. You have to rewrite these to look different but mean the same thing. So here's how I'm going to do it. For the first term here, I can take the derivative with respect to x of x squared. That's easy. But now I've changed the problem. So to compensate for that, I'm going to multiply on the back by dx dt. See what happens there? If you look at this and you look at this, they are the same. See how when you multiply the d dx by the dx dt, the dx's would cancel and you would just be left with d dt of x squared? So these two are the same. But now, by doing this, it allows me to do that front end and take the derivative of x squared. Now I'm going to do the same thing with y squared. So the derivative with respect to t of y squared I can't do, but I can do the derivative with respect to y of y squared, but I have to multiply by dy dt. And again, if you look at this and you look here, the dy's would cancel and you would just be left with d over dt of y squared. So now I can differentiate. So the derivative with respect to x of x squared is just 2x, but now I've got the dx dt behind, plus the derivative with respect to y of y squared is 2y dy dt, and this is still equal to 0. Now, what am I looking for? Well, I've got this equation, which now should involve this, and it does. You see that dx dt? You see the dy dt. I'm going to go ahead and solve for dy dt.
August 30th and are unhappy with your pictures, please bring your package with you and report to the auditorium. If you are a new student or a student that didn't have your photo taken or didn't purchase a package in August and would like to do so now, please bring your order form and payment envelope with you to the auditorium. Again, students in grade 10, last names M through Z. Thank you.
Okay, I just kept going here. What I did was I'm solving for dy dt here because that's what I'm looking for. So what I'm doing is using some algebra. I subtracted this guy right here. I subtracted him over to the other side to give me negative 2x dx dt. And then I just went ahead and divided both sides by 2y to cancel those and give me dy dt equals, I can cancel these, so I'm going to have negative x times dx dt all over y. Okay? All right, so there's my dy dt. Perfect. Okay, now I'm ready for my fill-ins and my solving. Okay, so let's go back up here. Let's do part A first. So part A, we were supposed to figure out how quickly y was changing, how fast the ladder was coming down the wall. At the moment, the base of the ladder was 3 feet from the wall. So I'm going to say here dy dt equals, okay, negative x. So negative, here it is, 3 times dx dt, which is right here, 0.5, divided by y. Okay, what's y? We don't have a y. We don't have a y when x is 3. So this is why I've got this little side work heading. So what I have to do is once more copy my equation, x squared plus y squared equals 64. When x is 3, I've got 3 squared plus y squared equals 64. Solving this for y, I have 9 plus y squared equals 64. I'm grabbing my calculator because I don't think this is going to come out too perfectly. Subtract my 9. 64 minus 9 is 55, so y squared equals 55. And then I'm going to square root both sides. So y is going to equal the square root of 55. Because that's not perfect, I'm going to leave it in the root to keep it more accurate. I only want to round a related rate problem at the very end. So y is equal to the square root of 55 when x is equal to 3. So for this y right here, I'm going to plug in the square root of 55. Now, if I put this into my calculator, hope you can see it there. I've got alpha y equals, get my fraction, negative 3 times 0.5 over the square root of 55. So dy dt is negative 0.202. I always want you guys to round to thousandths. So 3 spots beyond the decimal point, negative 0.202. And what this means is, at the moment, the base of the ladder is 3 feet from the wall. The top of the ladder is sliding down the wall at the rate of 0.202, and we know this is in feet per second from up top. Okay, let me bring that up here. So at the moment, the base of the ladder is exactly 3 feet from the wall. The top of the ladder is sliding down the wall at the rate of 0.202 feet per second. Okay. Now, we also had a part B. So that would be your answer for part A. Now, part B wanted how quickly the ladder is sliding down the wall when the base of the ladder is 4 feet from the wall. Okay? All the work is done. You don't need to redo everything. All you need to do is switch out the side work. So instead of the 3 squared, we'll have a 4 squared. We'll solve for the new y, and then we'll plug that new y into here for the y, and then we'll change the x. So for part B, so this was part A. So for part B, what I'm going to do is I'm just going to recopy dy dt is equal to negative x dx dt over y. I'm just bringing my dy dt down. Now, let's go to the side work, kind of give me some room here. So this was part A side work. This would be part B side work. It'll be 4 squared plus y squared equals 64. So then that's 16 plus y squared equals 64. And if I take 64 minus 16, I get 48. So y squared is equal to 48, and I square root. So y is equal to the square root of 48. It would be plus or minus, but the minus doesn't make sense in the context of the problem, so I'm just going to go with the positive. So down here then, I'm going to plug these in. So I've got negative 4 times my dx dt, which is constant, 0.5, divided by the square root of 48. And if I plug that into my calculator, I have negative 4 times 0.5 over square root 48. And I've got negative 0.289, negative 0.289 feet per second. So let me show you how this is going to change. Rather than have me rewrite this, you should rewrite it, but so the video isn't so long, what I want you to do is write this for part B. At the moment, the base of the ladder is 4 feet from the wall. The top of the ladder is sliding down the wall at the rate of 0.289 feet per second. Notice, even though both of my rates came out negative, that's just giving me direction. So the fact that I use the word down the wall is why I don't need to attach the negative in the sentence. Down means I'm losing distance. I'm losing distance at this rate. The distance is shrinking or decreasing. Okay, and last but not least, for part C, when the base of the ladder is 6 feet from the wall, then how quickly is the ladder sliding down the wall? And again, that's just going to take one more piece of side work. So this is getting kind of messy. The side work for part C, if you don't mind, I'll actually put it down here, right here, part C. The side work would be 6 squared plus y squared equals 64. So y squared is going to be 64 minus 36, which is 28. I'm going to square root both sides, and so y equals the square root of 28. So then my work here will be recopying dy dt equals negative x dx dt over y. So that's going to be negative 6 times 0.5 all over the square root of 28. And when I do that on my calculator, I get negative 6 times 0.5 over square root 28, negative 0.567. So negative 0.567 feet per second. So again, in order to save time, you can write the whole sentence out. Let me change colors one more time here. I'll go to red. Your statement for part C would say, at the moment the base of the ladder is 6 feet from the wall, the top of the ladder is sliding down the wall at the rate of, and I'll put it here, 0.567 feet per second. Okay. Tune in to the next video to see the finished product here and just a few other tidbits.